I know a ton of people go there to chase northern lights.
Yeah, I think there is this ongoing debate where it's best. There's Tromsø, and then there's like a place in
Abyssinian.
yeah, exactly. And then they both debate where it's better, where is more northern light. But then again, it's also about the overcast. So yeah, and I don't want to enter this debate. So I just say Tromsø was very nice, but probably other places are nice too.
I made the mistake the first time I went chasing. I went in the middle of winter in Iceland because also there was supposed to be this comet that was supposed to brighten like crazy. And then of course the comet, exploded and fragmented when it went around the sun. And it was completely cloudy because winter in Iceland is obviously just rainy, cloudy, horrible weather. So don't go chasing in the middle of winter.
Problem,
yeah. That's cool. Okay, well, yeah, I've seen an aurora from Southern California once when there was like a ton of solar activity almost 20 years ago, but it was not like the curtains of green light that you see in all these amazing photos.
But I think a lot of the pictures you have a wrong impression because there are so long exposure time, right? That they're often kind of cheating. But
yeah, the first time I saw them, I came back to the hotel and I saw them on my camera screen, and they just looked like kind of diffuse clouds. So yeah, obviously the camera sensors are way more sensitive than human eyes.
Yeah.
Yeah. Okay. All right. Well, let's get started. Max, you were going to give the first presentation because you're on the East Coast. Is that correct?
Yeah. Yes.
Okay.
Yes. Here in Baltimore.
Okay. Cool. All right. I will introduce you. Laura May, we'll see you in a few minutes after Max's presentation.
Yeah.
So Dr. Max Gronke is a postdoctoral fellow in theoretical astrophysics at Johns Hopkins University. His research focuses on understanding the dynamics of plasma in and around galaxies, which he does using basic theory as well as computer simulations. And Max, I believe you, in addition to being a postdoc, a Hubble fellow, this prized fellowship at Johns Hopkins, you're also starting in Germany as another position soon. Is that?
Yeah, in autumn I will move to Munich, to Garching exactly. That's at the Max Planck Institute for Astrophysics, and I'll start one of these group leader positions there. So start a small research group. It will be very exciting. I'm looking forward to that. It will be very cool, and
awesome.
Also looking forward to Munich. Heard it's nice to live there, so it will be cool.
Yeah, that's I envy you. I'll have to come visit because I want.
You should, yeah. Have a beer in a beer garden.
Yeah, absolutely. All right, well, I'll let you take it away with your presentation on plasma in the galaxy outskirts.
All right, let me try to share a screen. Okay. Right. Okay. I hope you guys see that. Yes. Yeah. Well, thank you so much, Cameron, for the introduction and the invitation. I'm very happy to be here doing an astronomy on tap. It's been a really long time. Of course, well, last time was in person, which is a lot of fun, but this seems to be fun too. So thanks a lot, Cameron, for organizing and inviting me. Before I should start, I should say I'm a theorist, so I might not be able to provide you with so many pretty pictures or videos people are used to in these kind of those lectures. And although Cameron said I should not put any equations on the slide, I couldn't resist to put one single equation, and I hope you bear with me and we see how it goes. I still hope I can entertain you in spite of this complication. All right, so the question I want to start with is, why are stars grouped in galaxies? And you see this picture here on the background, which is the Hubble Ultra Deep Field. And I don't know, some of you might have tuned in last time when Professor Jessica Work talked in length about the Hubble Ultra Deep Field. So I won't repeat a lot of this here, just that you see, more than 5,000 galaxies in the background here, each with millions of stars. So for me, it's always kind of a humbling image, right? You see all these galaxies, and each of the galaxy, so many stars, which means there are so many planets and moons. It's quite makes you quite small in a way. But for today, I just put up this image because you see that these stars are organized in these, well, islands of stars, these galaxies. And I want you to think about this simple question, you know, why is it like this? Why aren't the stars, you know, covering the whole sky? Why aren't they uniformly distributed? Why are they in these islands, in these clumps? And, you know, this has been, in fact, you know, quite old question. Already the ancient Greek, they thought about this question. Of course, they did not have good telescopes as we do. You know, they looked with their bare eyes, but they could see already, you know, the strip on the Milky Way. I'm sure many of you saw that. If you get out of LA in maybe the desert or something, you see the Milky Way across the sky. And there you also notice the same thing, right? There are some areas where you have a lot of stars, and then some areas, you know, where it's very few stars. So clearly, again, it's not uniformly distributed, but you have just this clustering of stars. And the old Greek, they came up with a quite interesting story of why this is an interesting theory, and that, of course, had to deal with gods. And it was that, okay, let me get this straight. It was that Zeus had a son, Heracles, and he wanted that Heracles had god-like abilities. So he let Heracles suckle on the breast of Hera. And I should say the son was not Hera's son. It was so Zeus is married to, or is the husband of Hera, but Heracles wasn't Hera's son. So clearly, when Hera woke up, you know, she was shocked seeing this strange baby on her breast, and she pushed it away. And, you know, in this process, milk spilled everywhere, spilled all over the sky, and that made, you know, this band of the Milky Way, and that's why we call it Milky Way. Now, you know, nowadays we have a bit more advanced theories. We, you know, we can simulate, and this, now I played the movie, simulates the evolution of the universe from, you know, very far back in time to today. And there you see how this, you know, clustering is happening, how stuff is pulled towards each other, and in this process, you know, forming galaxies. And of course, you know why stuff is pulled towards each other. It's because of gravity. It's just everything has mass in this video, and, you know, the when you solve the equations, things get pulled towards each other, and they form these islands of stars or galaxies. Now, I should say these kind of simulations are very expensive. They run on big supercomputers, and again, for those of you who have been here last time, Zach Haven, he talked a lot about these kind of simulations. I want to say, you know, a little bit more what gravity does, because gravity doesn't just, you know, pull things towards each other, but, and we know that, you know, from the time where Galileo Galilei threw down his metal balls from the Tower of Pisa, you know, in this process, it converts gravity to speed, right? Everybody knows that you drop down something, it gets accelerated, and so, you know, it gets faster, or we say, you know, it converts gravitational energy to kinetic energy, converts gravity to speed. And now, if you imagine, you know, that Galileo Galilei dropped, you know, not some metal balls, but a melon, what would happen is that, well, the melon would splash on the floor and be destroyed. And that's very similar in a way what happens in the universe. What happens there is that, you know, this gas is streaming in, it gets pulled towards each other, and then it crashes onto each other. And in this process, it converts then this speed to heat. So it heats up, this gas is being heated up. And, you know, if we can still observe this today. So this is a picture of a galaxy, but, you know, if we were to observe that in a different energy, and we can do that using, you know, an X-ray telescope with very high energy. X-rays are very high energy photons, and we can see that around this galaxy there is a lot of gas which is extremely hot, emitting this X-ray radiation, more than 1 million degree, surrounding this galaxy, quite you know, far away from this galaxy. And, you know, in fact, it's so hot that the electrons are not bound to the atoms anymore. Instead, you don't have gas anymore. You have this soup, of electrons and protons, and this soup that's a plasma. So plasma is the fourth state of matter. You have solids, liquid, gas, and plasma. And because the universe is so often so hot, we say that more than 90% of all visible matter is plasma. So this gas around there, I should say, it's not really gas, it's plasma. And that this is happening not just as for this one galaxy. You can see in this beautiful image here, again showing you this X-ray, very high energy radiation. And the picture here shows not just a single galaxy, but what we call a galaxy cluster. That's if kind of a clump of many galaxies. So it's kind of, if you think about a galaxy being an island of stars, this is more like an island of galaxies. So there are thousands of galaxies inside this galaxy cluster, and because it's so big, so massive, that means the gas is also hotter. If you think again about the Tower of Pisa, if you drop it from a higher height, you get more speed out of your gravity and therefore more heat. And so this gas here is not just 1 million, but between 10 and 100 million degrees. Now, the interesting thing, something interesting you can discover if you look at the same object with another telescope. And in astronomy, we got often asked, why do you need so many different telescopes? And that's one of the reasons, because we want to look at the same object in different wavelength, or looking at different energies, or different temperatures. And we can do that, and I'm sure many of you know this telescope, the Hubble Space Telescope, and look at the same object. I don't know if I can switch back. So that's an X-ray, and if I switch, same object, but with a different temperature, you see these interesting structure, these interesting filaments here, and these filaments only have a temperature of 10,000 degrees. So that's very cold gas, I would say, and many of you might say, 10,000 degrees is not that cold, but of course, compared to this 10 or 100 million degree we saw before, it's actually quite cold, right? Now, and these two images really visualize this big puzzle, I would say, we have around the galaxy and throughout the universe. We have this very hot gas, and just next to it, we have much colder gas. It's, if you think of it like, you think of a snowman standing, in lava. It's strange. How does the snowman get there in the first place? And why does it survive? Why doesn't it melt? And I want to talk a little bit more about this puzzle, because not just intuitively it's strange. Oh, sorry, I should say, it's not just happening around these galaxy clusters, but you have hot and cold gas, in many places in the universe. This is another image of a galaxy, and that's actually not just one image, but three images on top of each other. In this green or turquoise, you see stars. So that's the galaxy here. And then in blue, and I do apologize for the color coding, I don't know who came up with that. There you have the hot gas again. So this million of degree temperature gas in this interesting biconical outflow. So, you see blue gas here and here. And we think of this galaxy, what happens here is that, stars in the center, when they die, they explode in a supernova, and they push out hot gas. So we understand where this million of degree temperature gas is coming from. It's from the supernova explosion, creating this very hot gas. But then if you look at this red color here, that's again is much colder gas, 10,000 degree cold gas. So again, we have our snowman in lava puzzle also in this galactic winds, not just in these galaxy clusters. And that this is strange, having this very cold gas and very hot gas basically on top of each other, not just intuitively, but also from a theoretical basis. I will show you now. And the reason for why this is strange is that cold gas just as you would think, is being destroyed very rapidly by hot gas. And one of the reasons is that that cold gas gets mixed into the hot gas. And I show you, a computer simulation of this process here, where say we have a little blob of cold gas, and then it's being hit by a hot wind coming here from this side of this computer simulation. And you can think of this hot wind again coming from, say, a supernova exploding or some other hot gas. Or you can even say, this cold gas is moving with respect, to the hot background, for instance, in a galaxy cluster. And what would happen there is that, this cold gas, this hot gas hits the cold gas, and then, these we say hydrodynamical instabilities develop, and you see, it's being mixed. There's now some of this intermediate color gas, and just after some time, there's no cold gas left. And I said that this is intuitive. I mean, you all know this process, right? You put in some cold milk into your coffee, you mix it with your spoon, the temperature is also being mixed, right? You don't expect that it's still, half the cup is cold and half the cup is hot. No, you mix it, and, hopefully for you, if you put in enough hot coffee, you end up with a hot coffee afterwards, and you don't have any cold gas or cold liquid left. Now, there's another thing that's also destroying cold gas in a second process, and that are shocks. And this happens with, if these processes, the winds, for instance, are a bit stronger. Here I show you another video, which is the same as you just saw. So you have some cold gas here and some wind, some computer simulation that is the wind is coming from the left here. That's a video from Evan Schneider, the more violent wind. And you see, she ran this computer simulation, by the way, on GPUs, graphic cards. And you see, this shock really blowing the cold gas apart. So think of this just as some kind of explosion or something hitting, a house, and everything is flying away and being destroyed. So is the cold gas. Right. So, this is the basic puzzle, right? We see this cold gas everywhere in the universe. I just showed you, but on the other hand, we know, just from experience, so to speak, but also from these computer simulations and from calculations that, cold gas is being destroyed very, very easily. So, and I want to propose to you or show you one solution of this puzzle, and that has to do with zombies, or it's just, I want to take the analogy with zombies, because if you think of, and that's going to be the slide with the one equation, if you think about, you have a zombie apocalypse, and you have a certain time here, that's the left-hand side of this equation, the time for you to kill a zombie. If this is smaller, so that's a smaller symbol, then the time for the zombie to revive and get up again, well, then, the humans win. So for instance, say it takes you 1 minute to kill a zombie, and for the zombie to revive, it takes the zombie 2 minutes, then it's very easy for you, right? Whenever the zombie gets up, you just kill it again, and in the end of the day, the humans will win. On the other hand, if it takes you much longer to kill a zombie than the time it takes the zombie to get up again, for instance, say you have a old musket or something, you have to reload or whatever. Say it takes you 5 minutes and it still takes the zombie 2 minutes to revive, then it doesn't look good for you. You're gonna be killed sooner or later. So the zombies would win. And what does that have to do, with the problem I just described? If you think about our simulation again with the cold gas and the hot gas hitting it, but this time what I did is that I made this revival time of the cold gas much shorter. And now you see that in this tail here, the cold gas is collecting. It can revive before it's being completely destroyed. And so, you know, in such a simulation, we actually end up with more cold gas even than we started with. And at the end of the day, you know, cold gas, it doesn't really survive, but it's being revived. It's been continuously being destroyed, but in continuously also being revived. So, you know, in this simulation, for instance, this killing time of the gas is longer than the reviving time of the gas, and therefore, you know, we have, you know, the cold gas wins in the end. We have some cold gas, and so, you know, that's basically what I wanted to show you, is that if you see pictures like this from, you know, either galaxy clusters where you have hot X-ray shining gas and, you know, much colder gas on top of each other, or also from galactic winds. I know that Jessica showed this picture the last time here. Then, you know, maybe, you know, what's happening is that this cold gas is being destroyed, but it's also continuously reviving, and therefore we see it in the universe. And I really want to stress the maybe, because as I said in the beginning, I'm a theorist. So, you know, there's always a really high chance that some theories, and that's nothing else than a theory, they're wrong. And that's just how science goes. And that could be that everything I said today is wrong, but I still hope that, you know, I could entertain you a little bit. And yeah, I thank you for your attention.
That was great. I will definitely let that equation slide. That was a good equation. The killing time scale versus the reviving time scale for zombies. Excellent job. Thank you for sharing that with us, Max.
That was awesome.
Sure. Yeah. I hope it was fine. I don't know if it was the first time somebody showed an equation during your astronomy.
Oh no, I don't think it's the first time. I think it's the first time people have talked about zombies during one of us.
Okay,
but that's good. That's good. Yeah. It also applies to differential equations like that. Apply to all sorts of things, like the spread of COVID. You know, if the time scale at which you infect someone else is shorter than the time scale over which, you know, you get well,
right.
then you're likely to spread that disease exponentially or whatnot. But I prefer the zombie analogy.
Yeah, I thought everybody heard enough of COVID, so yeah. It's
okay, so there are we encourage people in the audience, if you have questions about Max's presentation or the relevant science, or even unrelated, I guess, we can field questions on general astronomy questions if you have them, and the same goes for Laura May's talk. We encourage you to ask them in the questions section or the comment section of the YouTube chat, and we will try and address them. There have already been a handful of questions asked. Let's see. Can you say anything about the net charge and charge distribution in hot and cold plasma settings?
Oh wow, yeah, that's a very deep question, actually. That's a great one. So, you know, so that's a really good point, because, you know, as you said, that if you are in such a hot medium, right, that you rip your electrons away from your protons, it can really happen that you have some net, you know, a lot of clustering of electrons here, and then, you know, there is a negative charge here overall, and, you know, it would be a positive charge over there, and then that would lead to some motion and actually some wave-like pattern, and that's a very interesting dynamics. You know, I should say in these simulation I presented today, it's assumed that, you know, this kind of things are not happening, and it's what we call ideal MHD, and so you know, we treat it in a bit more simple way. It's much more gas-like. You know, what's happening in the real universe? I mean, there's certainly regions where these effects matter, but you know, not necessarily in these things I showed today. Just because, you know, these things are relatively large, and therefore we think it's more or less well mixed.
Well balanced, yeah.
Mm.
Yeah. Are there definitions for hot and cold gas plasmas, i.e. like the boundary temperatures associated with these different phases or whatnot?
Wow, that's again such a good scientific question. I should have made my talk much higher level with this audience. I should have gone much more in detail. Okay, so so these observations, what I talked today, right, was this million of degree or hotter and 10,000 degree Kelvin, and that's basically defined in an observational sense first of all, because as I said, we saw this X-ray, and that's this million of degree temperature gas or hotter, and then we saw these other images that was Balmer lines, they're called. So it's essentially hydrogen emitting, and that's 10,000 degree Kelvin. So that's a pure observational definition. Then there's even colder phases. If you go to even different telescopes, for instance, you might have heard about ALMA, that's huge dishes, and then you see molecular lines, which are even colder, 100 Kelvin or so. So that would be the observational definition. I might just add the theoretical definition too, and that is if you essentially compute how stable such a gas is, if you heat it a little bit, and then will it heat further, or will it drop down to its original temperature? And that's also these temperatures I was mentioning, 1,000,000 degree and 10,000 degree, they're also chosen because these are stable temperatures. So the universe automatically distributes in these temperatures because they're stable, and not in these intermediate temperatures because they're what we call unstable. I don't know if that helped, but I mean, such a deep question. I could also give a bit more technical answer, I think.
No, it's a good question. It's a very good question. We just had a program that Max and I were participating in that was a 2-month-long program on studying these effects and studying the behavior of this gas in the outskirts of galaxies. And our two speakers at the last month's Astronomy on Tap that Max referenced a few times, Jess Work and Zach Hafen, also study this. And so this was one of the kind of key issues, is like, what is the temperature range of the phases and the phases of the gas that we find throughout these components, both from observations as well as can we theoretically motivate their formation structures.
Yeah, and it was supposed to happen in Santa Barbara in winter, so I was very much looking forward to getting out of Baltimore. Instead, I was stuck in Zoom for hours, which was great, but Santa Barbara on the beach would have been even greater.
Yeah, hanging out at the beach in Santa Barbara is better than hanging out in an isolated room on a Zoom call in Baltimore.
Definitely.
You can agree with
definitely.
To respond to the most recent question, just for confirmation, yes, this is the gas in galaxies, in the outskirts of galaxies for the most part. Sometimes in between them, but more we're talking about in between them. You don't usually find the densities necessary to get this, although, yeah, I guess the IgM can have filamentary structures that you form cooler gas, but more of this behavior occurs in the outskirts of galaxies.
But also inside galaxies, actually. If you think about the structure between stars, right? If you think about, you have stars exploding inside galaxies, there's also a lot of gas there. And there, you also have hot and cold gas actually really close to each other. And there's a lot of interesting, similar dynamics than I just showed going on. And that's the beautiful thing about these kind of equations. You can really relate them to every different setups. You don't have to re-simulate every setup. I think it's quite nice. That's what I love about these equations, or equations in general.
Okay, 2 more quick questions, and then we will move on. Are there any other factors, such as the age and size of a galaxy, which influence the rate in which cold gas gets revived, much like those zombies?
Yeah, so your audience are all pros. I mean, so age and of course age and size of galaxies is really are relevant parameters for how the whole system looks like, right? So you say if you have a say you have a very young galaxy, then there is a lot of stars exploding, because the big ones, they don't live very long. They explode basically straight away. And then you push out this gas and you get these beautiful images, what I showed of these galactic winds. So you have a lot of these dynamics going on. That being said, the time span for this gas revival is purely a function of the properties of the gas. So that's actually plasma physics kind of property. So, the gas itself, it doesn't care about where it's coming from. So the answer to this question is kind of both ways.
Yeah, that's good question and good answer. It's a tricky one. And then I like this question, kind of related, kind of not. Speaking of COVID, corona, I guess, will plasma physics solve the coronal heating problem around our sun, theoretically or observationally and experimentally, via the Parker Solar Probe, or both, I guess? So obviously this is somewhat distinct from the talk you were talking about, but is related to plasma and hot gas and corona, the solar corona, the crown of the sun.
Right.
I personally would have to say, like, we haven't been able to do it. Plasma physics hasn't been able to solve it yet, theoretically, without additional observational constraints. So I think, but observations alone won't necessarily be able to do it. So I think, yeah, it's a combination. The Parker Solar Probe, which is this mission that's getting super close to the sun and trying not to melt, will be able to measure the composition and the temperature and how it varies in close proximity to the sun in the solar corona. And that will provide additional constraints that maybe we may be able to use in plasma physical models to figure out, like, are there acoustic waves that are heating up the corona or that sort of thing. But I don't know. Do you guys have anything? I don't like,
right.
I'm a specialist on this, so that's what I think, but I might be wrong.
No, I mean, particularly for the coronal heating problem, I'm also not a specialist, and I can't comment on that. There's one interesting thing I think about this whole problem, which actually relates to my talk. So I'm just going to mention it real quick, right? Because we had this hot and cold gas really close to each other, right? And you also find that again in the sun, but this time kind of reverse. You have this hot corona more further out, and then you have this coronal rain, which is actually much colder than the surrounding again. So you might actually apply similar dynamics or similar thoughts to this problem, because you have this cold gas falling down, right? So it's also kind of a question why, how long does it survive? Why does it survive that long?
Yeah. Some more great questions. We will try and address them later tonight, but thank you very much, Max. Excellent presentation. And
pleasure.
And we will move on to Laura May. I'm excited about this.
It's going to be a very different
show. Oh no, that's good. That's good. That's why we get different speakers to talk about different stuff. This is going to be awesome. All right. Laura May Abron is a French-US science communicator. She studied astrophysics at the Paris Observatory and has appeared as host and writer for several science shows, including the recent climate change app called One Step. She runs a group for women interested in science, makes art related to astrophysics, and recently completed a large artwork about spectroscopy. And in her spare time, she likes to chase aurora, eclipses, and tornadoes. Sounds like some awesome activities to chase.
It's good. The U.S. is a good place to do it.
Oh, is it?
I mean,
yeah,
tornadoes.
Alaska.
Tornado chasing primarily, storm chasing, etc. The U.S. is kind of the main place to do it. Some friends of mine wanted to go down to South America to do it. But yeah, the U.S. is kind of the main place to do that. And for Northern Lights, obviously Northern America, so Canada is a good place to do it. And eclipses, that unfortunately it's everywhere.
Yeah. That's it. So are there not tornadoes as prevalent in other, I guess I don't know, I think of the Great Plains and
yeah,
Oklahoma and
like
such.
the way tornadoes form is facilitated by the US geography, basically. So you really have Tornado Alley has this really wonderful kind of, you've got the warm air and the cold fronts that kind of intersect, and that means that it's an optimal place to form tornadoes. And then they kind of migrate upwards throughout the season. So we consider that season begins around April. Of course, there are tornadoes before, but then it kind of migrates upward. So I chase sometimes with some friends from Canada, and so they can, they'll come down to chase, and then they kind of finish the season up in Canada. But there are tornadoes, bizarrely enough, there are tornadoes, and there have been several tornadoes when I was in the area of Venice in Italy. Little tornadoes. And there was another, I think there was a tornado in France a couple months ago. So there are some baby ones in Europe and in other places, but they just don't occur as frequently again, it's to do with geographical parameters and all sorts of, similar to climate change, it's a lot of systems and a lot of things that, whether it's currents and airflow and oceans and et cetera. So yeah, it's a whole other topic, and it's an awesome, tornadoes are a really interesting topic.
Oh, cool. Well, maybe we'll have to have you back to talk about tornadoes. Tornadoes on other planets.
Oh yes, in fact there are dust devils. If you guys want to look up the video, there are dust devils on Mars, and we actually have a kind of a animated video image of it. I can't remember what captured it, but there are some dust devils. There are some images of moving dust devils that look like baby tornadoes on Mars.
Cool.
So,
very cool.
Pretty cool.
Okay, well, I will let you. You're going to talk about astronomical sources for potential sources for climate change, right?
Yes.
Yeah.
Yes,
okay. Cool. Well, I'll let you share your screen and take it away.
Cool. All right. Okay. Am I? No, not yet. All right. Sorry, I don't use Zoom very often. Cool. All right. So my talk is entitled 2021, A Climate Change Odyssey, and that's because I want to tell you about the odyssey that is climate change. And that means we're not just looking at the present, but also at the past, and even at other planets, and basically everything going on around us. So my background is in astrophysics, but it's actually been super useful foundation to investigate climate change research, right? I am not a climatologist. I'm just telling you this up front. But there's a lot, there's a lot to gain. And obviously NASA actually funds a huge amount of climate change research, satellites. So the two topics are actually pretty well connected. So presently the Earth has been undergoing rapid climate change, which translates to a rise in our current global average temperature of 15 degrees Celsius, which is about 60 degrees Fahrenheit. So this graph is just showing you this kind of increase in the average temperature, and this is the temperature anomaly, so the deviation we have from this average temperature. So the Earth doesn't exist on its own, right? It's subject to a lot of influence from the solar system. And whether that's the sun, of course, massive planets like Jupiter and Saturn, and even our moon, or comets and asteroids. And all these effects, in turn, have actually altered our planet, other planets, and our climate. So here's just to show you a little example. I mentioned Saturn and Jupiter, the two biggest planet in our solar system. So is climate change caused by natural phenomena? It's a perfectly fair question to ask. Now, climate change is actually nothing new. So Earth has actually gone through large variations in climate and changes in global temperature. So here you've got the 5 major ice ages in Earth's history. I've put in the dinosaurs and the end of the dinosaurs and the approximate start date of hominids, humans, so that you can kind of get an idea that these things were happening long before us. And so we actually have a lot of clues about this. We can date rock formations and know what conditions they might have formed in. We've got deep sea sediments, and we also have ice cores, which I thought you might want to know that they're called carats in French. We call them carottes glaciaires. So again, we can extract these from deep within glaciers, which haven't melted in millions of years. And so the deeper the ice, the further back in time we can go. And not only does the ice tell us kind of about past climate, but it also has tiny little air bubbles that we actually extract. And then we can actually sample past air from millions of years ago, which is incredibly cool. So we have all sorts of other little clues. So I'll show you a couple. So we've got rock formations, like I mentioned. We've got deep sea sediments, which is similar to the ice cores. And we've got the ice cores. We've got tree rings. So just the rings in trees. And we've also got fossils, the fossils of shelled organisms, calcium carbonate, silicon dioxide, what they're made of, and all this put together that allows us to paint actually a pretty accurate picture of our past climate, and it is the focus of paleoclimatology. So on this image, you've got, I believe that's a deep sea sediment core. So the estimate that we've also got.
I think your sound sounds garbled on that. Oh, mine.
Oh, is my sound bugging? Because I can plug in my earphones.
Yeah, I think we should try.
Yeah, let me put in my earphones just because occasionally sound. Is this any better?
Yeah, that sounds great.
Okay, fantastic.
I think that addressed it. Sorry.
Fantastic. No worries. Sorry about that. So interspersed in these ice ages, we've actually also had other little periods of interglacials and glacials, right? So we have had a lot of variations in climate change in the past. So it's perfectly fair to ask, again, is it caused by natural sources? And here are some causes of past climate change. So we've got continental drift. That's that image with all the continents together. We've got volcanoes, mass volcanic activity, and we've got asteroids. So for example, we think that dinosaurs might have actually been killed by not the asteroid itself or the tsunami, but the dust, basically, that would have been in the atmosphere that would have caused climate change as a result of this impact. And there is another major reason, which is Earth's orbit, right? So Earth goes around the sun. It takes 1 Earth year in what we call an orbit. And that orbit has a variety of defining features. We've got how circular it is, Earth's tilt on that orbit, the direction and orientation that that orbit faces. We've got a couple of other parameters, which I'm not going to go into because we would spend all night doing that, but I'll look into them in detail. So Earth's tilt is basically what causes our seasons. This is also called obliquity. And the two hemispheres get different amounts of sunlight at different points of the year or different points in our orbit. And that tilt actually changes. So currently our tilt is 23.4 degrees, but it actually varies between 22.1 and about 24.5. So you can see here, you've got this little variation in the angle, and this will actually change quite a lot, the amount of sunlight that we receive and our general seasonal patterns. Next, we've got how circular our orbit is. And this also changes. And it's called also a planet's eccentricity, which is a value that we estimate from 0 to 1. So when an orbit is less circular, you get a more flattened circle, and that will create big differences in basically how far away a planet will get from its star for part of the year and part of its orbit. Earth's orbit is super, super circular. And that's basically, it translates to a difference of only about 1.5 million kilometers when we're at closest or furthest approach from the sun. It's 0.0167. So here are just the eccentricities of the planet and the solar system. So again, that's how circular their orbits are. So just to give you an idea for comparison, you'll see that we have very, very circular orbits. And this likely contributed to the stability of our solar system, the development of life on Earth. You'll see that obviously we've got Mercury is around 0.2, everything else, Mars is around 0.1, everything else super, super stable. Now we do find exoplanets, which have very, very eccentric orbits. I'm not going to get into that different subject, but it can lead them to being potentially captured by other stars, disrupting other planets' orbits. There's even a very cool exchange phenomena that I like through the Lidov-Kozai mechanism. So just to show you, this is a very, very eccentric orbit of a planet called HD 20782b. Now, just to clarify, this is a planet in another solar system, but it's just been put next to these other orbits. So you can kind of get an idea of what its orbit looks like. It's nothing like our planets, and its eccentricity, which again was from 0 to 1, is about 0.96. Now that eccentricity does change just a little bit, but it's enough to actually have an effect on our climate. Next, we have axial precession. Earth has a little wobble. I'm not going to get into the details of this because, again, it takes a long time. But yeah, just think of it kind of like a spinning top, and that's the kind of movement. So we've got a change in orientation. So just to show you what it looks like. And again, that will change some things with regards to northern hemisphere and southern hemisphere and when we get the most illumination. There's all sorts of other really interesting movements like nutation. And again, we could talk about this for a very long time. So these collective effects were put together by a Serbian mathematician, astronomer, and geophysicist called Milutin Milankovic in the 1920s. Now, he spent about 30 years working on what is now called the Milankovitch cycles, and it's kind of like a climate time machine. So he calculated the interval at which ice ages occur based on all these differences in our orbits. And and so after his death, a lot of this research after the 1950s, a lot of his theories were validated. We do need more research to kind of understand the mechanisms that cause the changes in Earth's rotation and how they kind of combine. But the theory that they drive the timing of the glacial and interglacial cycles is pretty generally accepted. So here's a summary. So again, just to show you this, this is going to be the change that we have in solar radiation, will change depending on the tilt of the Earth, for example. And so how does this cause climate change? So essentially, this triggers an initially relatively small temperature change on Earth. This can melt permafrost and have other changes that are caused by the warming that release CO2 into the atmosphere. And because CO2 is a greenhouse gas, increased CO2 concentrations cause more global warming. So, okay, you may be wondering, well, what about what's actually heating us and what's at the center of our orbit and the center of the solar system? And that is the sun, right? Now, the sun heats us because of also the greenhouse effect. It would actually be much colder on our planet if we didn't have the atmosphere. Essentially, our atmosphere traps some of the heat that we get from the sun and allows us to have a current average temperature of about 15 degrees Celsius. And I've just explained basically how that works. So again, it's perfectly fair for someone to ask if our star is for some reason giving off more luminosity and more heat. There are variable stars out there whose brightness will change for a lot of different reasons. They might be swelling and shrinking, some pulsate, others have huge flares, or sometimes it's just part of their normal evolutionary cycle, a change to supernovae. Or for example, here's a star that is I believe it's a red giant. So again, we can see some differences in size here, and obviously then differences in brightness. So is the sun a variable star? Yes and no. On short-term scales, yes. On very short-term scales, the sun is variable, but not long-term. The sun has an 11-year cycle. Again, if you chase the northern lights, you will be aware of that. And so the difference in activity we can see mostly through sunspots, for example. Don't look at the sun directly, obviously. But here we've got an image that shows the difference between solar minimum when the sun is least active and solar maximum when it's very active. And you can see all those little sunspots. So here's a picture in the UV. We've got some nice little magnetic field lines here that are coming from some of these sunspots. And you can see that there's a difference in activity, essentially. But here's the thing, the difference in energy that we actually get over this cycle only varies by about 0.1%. So the sun is a dynamic body, and the main variability we actually see is sunspots, but it just doesn't vary enough to have that big of an effect. Now, we've actually measured and tracked the amount of the sun's energy that hits the top of the atmosphere since 1978, right? Using sensors on satellites. And there's just been no upward trend in the amount of the sun's energy that reaches Earth. And this is the thing. We've actually been going through a period of very weak solar activity and output, which had also one of the lowest levels of sunspot activity since record keeping began. So this is just a plot to show you. So you've got the number of sunspots here, and the more sunspots, essentially, the more active the sun is. So this is cycle 24 is on the right, which just ended, which was a very frustrating time for people who chased auroras. I mean, there were a couple of nice events, but the sun has been actually quite quiet. So the temperature spike in the last 50 years just can't be explained by a change in solar energy output. So again, this is just to compare the amount of energy we get from the sun and the temperature. And you can see those are going in kind of either different or certainly right now opposite directions. So, okay, we've looked at the sun and we've looked at Earth. What about other planets in the solar system? And how about our closest neighbor? So yes, the sun is not going to help us either way towards solving or accentuating climate change. So Venus is a very interesting planet because it's actually the hottest planet in the solar system, right? So it's a scorching 470 degrees Celsius there, which is about 880 degrees Fahrenheit, I believe. And it's not the closest planet to the sun. That's Mercury. So Venus is actually a very good example of this greenhouse effect I was telling you about earlier. And it has what we call a runaway greenhouse effect, a little similar to ours, but much, much worse. So here's a picture from the surface of Venus that was caught by the Venera probe that was sent by the Soviets. I can't remember what year, maybe the 70s. So you can see it does not look like a hospitable environment, and it has that very, very thick atmosphere. So, but here's what Venus might have looked like in the past. We actually think that Venus might have had oceans, continents, and it might have looked a lot like us, right? So we have had this runaway greenhouse effect that occurred in between, and there's a variety of theories as to why that happened. Now, it's possible that the sun just got a little hotter in the early days of the solar system, and that's just part of its natural cycle, and that could have made the oceans evaporate, which then also water vapor is a greenhouse gas. Venus also has a very strong electric wind that might have separated and pushed out the water molecules, or it might have gone through a very catastrophic one-time event, like something slamming into it, which basically caused a lot of magma to surface, a lot of CO2 to be released, and the entire surface has been resurfaced. So that means that essentially we don't even have a lot of craters on there because the surface is very new. Either way, its oceans evaporated, and we know that that happened probably because of a process that is very different to Earth. So again, Venus is not really a great example. So what about other planets? So here's just to show you a beautiful illustration of the electric wind. So we know that there are magnetic fields and there are also electric fields, and Venus has a very strong electric field. So we think that could have been responsible, and it does have an atmosphere that's mostly CO2, unlike ours. So how about Neptune? Have we observed any heating there? We actually have. We have observed heating on Neptune, and part of the reason we know this is because of this growing cloud cover. So these are some images that have basically an average of the clouds on Neptune, and we've seen a growing cloud cover. And now this is because it's actually summer on Neptune. So Neptune also experiences seasons because it's also got an axial tilt. And it's actually quite remarkable that it experiences seasons because it's 40 times further away than us from the sun, right? So again, this is happening, but here's the thing. We've been observing this for quite a while now, and Neptune being that far away from the sun, it has a very, very large orbit. So this is just to show you the orbit that crosses Pluto's orbit and where it is on different years. So Neptune's orbit is 165 Earth years, right? So a season lasts about 40 years. So right now we are actually seeing summer on Neptune. And so it is normal that it's heating, and it's just that it has much longer seasons than we do. Okay, so we've actually looked at a lot of different things. We've even looked at cosmic rays. There's some convoluted theories about cosmic rays. So cosmic rays, just to clarify, are high energy particles that are moving through space at close to the speed of light. And they can come from supernovae, from solar flares, generally very high energy events. Now, our magnetic fields actually protects us from most of them. And so there's this convoluted theory that cosmic rays can seed or create clouds, which then reflect sunlight. So fewer cosmic rays mean that we have fewer clouds and more light and heat hitting the Earth, which would cause a warmer climate. This is just, yeah, the major problem with this theory anyway, is that the amount of cosmic rays that have been hitting us is actually up. So again, there's just kind of no correlation there. We've actually even looked at moonlight. This is an article published in Nature from 1999 that I found. So I can assure you that people have looked at every possible cause in our spatial environment. It's actually very interesting. You can learn all sorts of things. So here's a paper on moonlight and global warming, again from 1999. So if the Earth's average temperature, so here's just to summarize the influences on our climate. So we've got the sun, we've got the shape, direction, orientation of our orbit. We could have the moon. We have cometary dust, which is similar to volcanism when we've got mass volcanism happening, which will fill the atmosphere again with dust and block out some of the light, and similar with asteroid impacts. So we've got all these potential influences, but the problem is that all of these things act on very, very long periods of time, right? So is it aliens? It's probably not aliens. Again, it's probably us. And here's to show you the main difference between all those instances of climate change, which take tens of thousands of years in the past, and our current one, which is that it's happening extremely fast. So these past ice ages and these past glaciations, we basically had global average temperatures rise by about 4 to 7 degrees Celsius, taking place over about 5,000 years. But in the past 100 years on Earth, the temperature has actually gone up by just over 1 degree Celsius. So this is 10 times faster. And if you're wondering if we're actually, if the Earth's temperature is rising, are we about to enter an interglacial? Well, we're actually not. Believe it or not, we're actually leaving an interglacial period that started about 11,000 years ago, we think. So this means Earth should actually be getting colder, not warmer. And it is itself part of the ice age that we are in. So in a way, we're actually quite fortunate that this is happening now, because it's not happening at a past period in time when it would have been by default much warmer on Earth. So I can tell you that the warming is not coming from astronomical sources. It is coming from us. Thank you.
That was a great reference to a classic horror film. Dream. That's excellent. Thank you for that presentation, Laura May.
I hope that wasn't too much information being thrown at people.
No, that was great. So yeah, we encourage people to ask questions in the YouTube chat, and I will try to find them and ask them of Laura May. And yeah, they can be related to the content of the talk, or we can also try and handle some additional questions on whatever you might be curious.
Aliens, for example.
Like aliens.
I don't know anything about aliens, I'm afraid.
And then after that, we'll get to our Astronomy on Tap pub trivia component, which is always super fun. Okay, so let's see. So a question: what causes this variability in the sun? Do we understand that?
Do we understand what causes the variability in the sun? Well, the sun has this cycle. I'm trying to think. Do we know what causes? I mean, it's got, they've got this, there's this switch in magnetic field. And actually it's 2 11-year cycles. So it's a 22-year cycle that we've got this switch in polarity of the sun. I believe that's just part of the natural, I think, driven by convection, probably.
Yeah. It's I can
please chime in. Yeah, please chime in.
I don't think it's super well understood.
Yeah.
It's definitely understanding the interior and the dynamics of the interior of the solar body is an active field of research. There's something called the alpha omega process that essentially defines, basically you have differential rotation of the interior of
that's right.
sun.
Yeah.
There's a
And that,
shear from one layer against the next, and so it
and
causes
it twists the magnetic field lines.
exactly.
Yeah.
And it twists the magnetic field lines, which erupts in this cycle. But again, that's kind of a glossing over of a really, really complicated subject. And yeah, I'm not a heliodynamicist, but I know that this is not like, people are not like, oh yeah, we've figured out the sun, let's move on to the next question. Like, this is,
I mean, it's like the corona problem. You know, obviously we've got a much hotter corona than we have the surface. So I guess the sun, like Jupiter, is the same. We don't fully understand how Jupiter works completely on the inside. Those are all active fields of research, which in fact I do want to advocate. I wanted to mention it for Venus. Venus is poorly understood, and there's so many theories just about, you know, how did its oceans evaporate? Why? Why does it has this gigantic electric field, this very dynamic electric wind? And, you know, I think people are so focused on Mars and they don't really want to send missions to Venus. And Venus is super, super interesting. And there's a lot of stuff going on there.
Another question. What are your thoughts on climate change decreasing the strength of the Gulf Stream, and what like possible side effects might that also play?
Yeah, so obviously, I think some of you guys know, we try to avoid using the term global warming because obviously climate change produces changes in climate. So there are places that might get warmer and some that might get colder. One of the places actually in the US, or one of the places in the world that suffered climate change the hardest, is in Alaska. There's a place we talked about this average, we've got currently an average rise of about 1 degree Celsius. And a place like Ukjavik in Alaska, they've actually had a rise in 7 degrees Celsius temperature. So yes, we do think the Gulf Stream, there is a large amount of data that indicates the Gulf Stream will probably shift. I mean, climate change is as someone pointed out when I gave this talk a week ago, it's a systems problem. There are so many things that factor in to climate change as an issue. And so, you know, there's so many simulations and there's so many models that can explain certain things. And we do know it's happening. For sure, climate change is happening, and it's because we're burning fossil fuels. But the consequences of it, you know, there's a lot of fine-tuning variability in it. The Gulf Stream, again, potentially could stop, and that could freeze the north of Europe. The north of Europe has been frozen in the past. So yeah, it's certainly a possibility that the Gulf Stream would basically be diverted. And I think, in fact, it might be diverted up to Greenland and places like that. And then we've got polar amplification. So, you know, everything that kind of happens at the poles gets amplified. So yeah, there's the second you switch one tiny little dial, everything else, there's just such a knock-on effect, which is, you know, it's interesting because when you look at these astronomical sources, they're actually pretty weak changes, and they only have really this big effect. For example, as I was showing you the Milankovitch cycles, when all those things coincide, then we've got a much bigger effect on climate change. But otherwise, it kind of, you know, it's very minor effects compared to what we're doing.
It's pretty interesting that he figured this out so long ago.
I know. And I was digging into it to try and understand how, because he spent 30 years doing this. This isn't something that he spent, you know, a year on and put out a paper. Milutin Milankovitch, yeah, so he was a mathematician, an astronomer, a geophysicist, and lots of his stuff was not confirmed of his living. And then, you know, a couple of years after he died, all this stuff was kind of confirmed. But mostly, I think he came at it from mathematics. So he made all these mathematical models. He included things like, again, solar insolation, the amount of sunlight we receive, all sorts of super interesting things.
But what year did he was doing this in, like the late
1920s? Yeah, he put this out this 1920, so 100 years ago.
That's awesome.
Yeah, super interesting.
Awesome. Okay, a couple of other good questions. Is there any known cyclical variation in like volcanic activity that we have, or geothermal activity that we have on the Earth that you know of?
Non-cyclical variations.
Are there any cyclical, like
right,
that, you know, we were talking, you're talking about, you know, cycles in the solar luminosity, although are there similar ones that occur on the Earth?
I mean, so obviously volcanic activity is, ongoing, active. There is, in fact, something just erupted in Iceland a couple of days ago. I just want to give a shout out to Iceland because we've all been watching the live feed of this volcano in Iceland. So that could be considered cyclical. And that's also because obviously we've got tectonic plate activity, which, for example, Venus has tectonics, but it doesn't have tectonic plates. So it's kind of got a different system. I mean, the cyclical nature of some things can also really be the fact that we've got these kind of knock-on effects on, once X happens, then Y happens, et cetera, et cetera. So again, like I was mentioning, polar amplification, for example, once we've got more ice covering the poles, then we've got more light being reflected. But again, I mean, I understand the question in terms of is there anything cyclical? Not on par in the same kind of way. You'd have to double check with obviously people who, volcanologists. I'm not sure how cyclical volcanism is, but yeah, I mean, again, it's more of a systems kind of interacting with each other than it is cycles in that way.
Interesting. Okay. The question related to your work in science communication. Your experience and opinion, which is more effective in science communication generally, presentations or art or narrative?
Ooh, good question.
I know, this is a good question.
This is a great question.
Narrative compared to presentation?
Well, narrative, like perhaps like, you think that the question is like narrative art in a presentation? I took it as like three different things, like narrative, like a narrative story or an article that goes through a narrative, but maybe the question did mean specifically within a presentation.
I mean, humans psychologically, I have done some amount of studying as to the psychology of what people are interested in. There are certainly things in science communication that you don't do, like telling people that a question is stupid or that a view is stupid. You don't ever do that. You think, oh, well, let's investigate that. But, at the base of, I think, human psychology is storytelling. So people respond well to fundamentally what is storytelling. And so that's applicable to anything, whether it's a presentation, whether it's art. I have been lucky that I've found that my art, which really is based on like theories of cosmology, I just did this really big piece for a creative agency in New York that again was based on spectroscopy, and it makes people want to learn about that in a way that I think if I was just like, here's how spectroscopy works, I don't know that they'd be that interested. But when you really kind of, enthusiasm obviously is super important, but really I think there's a storytelling aspect in all these things. And when you make things accessible to people and you tell them, here's how we know this, and this is accessible to you, because it is. All of this information is accessible to a lot of people. And I think a lot of people think, oh, well, I don't know if I can figure this out, but yeah, it's all accessible. And having an element of storytelling, I think, is super important as to how we know this and how we've discovered these things. And yeah.
There was a request about your art.
Oh.
What is your astrophysics art like?
Oh, lots of. Do I have some here? I think I have some here. Let me see. I do have a tiny little piece here. This is a very old one. This is one of the first ones I made. This is, I don't know if you can really tell that. So this is one of the things I make is cosmic entomology. So they're actually based on real butterflies and entomology. And then I've got a lot of symbolism to do with telescopes. So I've got a lot of mosaic work that's embedded in them. So that's one aspect of the things I make. And, I have one that's based on the Big Rip theory of cosmology. That's kind of like a theory of the end of the universe. And then I do a lot of paintings that are based on sometimes simulations, kind of like the stuff that you do. And then, yeah, I just did a big piece on spectroscopy. It's on my Instagram and website and things like that. And it's kind of abstract based. And again, I think, having an a lot of things in cosmology and astrophysics are super abstract. A lot of ideas in science are abstract. So I think when you can kind of give them your own interpretation and think about them for a while, that's kind of what I try to do with my art.
Yeah, I dig it. Okay, let's see.
Thank you.
Oh, there it is. Okay. Sorry, I'm getting all mixed up with everything. That argument was awesome. I love the butterfly.
Oh, thank you. And they're all my butterflies are modeled after actual butterflies. So I actually have to do a lot of research on sizing. So I look up I have a lot of entomology books and a lot of butterfly things to find the exact size of some obscure butterfly in Papua New Guinea. Discovered recently that there's a butterfly named after the Northern Lights called Alcides aurora, which I am desperately hunting because it looks like it's got a little aurora on it. So yeah, there's lots of interesting things in the natural world and in the natural history and animal realm and all that stuff. So
cool. Awesome. Okay, thank you for the presentation. Thank you both of you for your wonderful presentations.
Thank you.
Let's move on to the trivia component
Ooh.
to our Astronomy on Tap event. So audience members, this is an opportunity for you guys to shine and to show your knowledge of the cosmos and whatnot. I'm going to try and share this. Let's see if I can do this. Okay, so can you guys see my slide here, this Astronomy on Tap slide? Okay, so audience members, go ahead and go to this website at the top, menti.com, and then type in this code. And that will allow you to answer the questions as we put them out there. I encourage, if you guys want to, Max and Laura May, you guys can feel free to. Heck, I'm gonna go there just to make sure this works the way it's supposed to.
I typed minty.com for some reason.
Oh, Minty. Yeah, I don't know what that is. Is that like a porn site or something? Hopefully.
Probably. No, I didn't load it. Let's see.
Okay,
Minty.
yeah. Don't go there. I don't know.
Don't go to Minty. It's just Menti.
Menti. Menti.
Cool.
Okay, yeah, it's working. Great. Okay, so everybody go to that website and I'll go through the questions and then you respond and we'll be able to see the responses as they pop up. All right, the first question. The NASA Mars Perseverance rover carries with it a helicopter. About how heavy is that helicopter? And a few different options here. So what do people think?
I feel like it's quite misleading to call it a helicopter because it is kind of more like a drone. I mean, I know I spoke about it to everyone and called it a helicopter, but Ingenuity.
Yes, Ingenuity is its name. And I encourage people to actually make their guesses without going onto the internet. I realize you're on a computer.
It's like classic pop trivia honor, right?
Knowledge. It can be very tempting to cheat, but I promise there's nothing to be gained. I'm not going to send you a prize if you're right. Don't cheat yourself.
Yeah.
I appreciate you putting in grams for us Europeans.
Oh, just trying to mix it up, you know.
Yeah.
Nice.
The metric, we appreciate the metric.
Yeah, 40 grams. It's like 1.5 ounces, which is like 1/10 of a pound, I guess.
It's very, very small.
Very convenient, this system you guys have.
So yes, the correct answer is indeed 4 pounds.
Oh.
And this is a really cool video that I found. All right, let's play this thing. It's a bit long. This is an animation. This isn't real footage from the surface of Mars. Although hopefully we may have that at some point. We saw the previous footage from the surface of Mars, which was pretty badass when it landed. So yeah, this is Perseverance stepping away. It set down its little friend. Hey, friend. Hey, Ingenuity. And then it stepped away so it can do its thing. And oh, here it goes. Turn those rotors around.
You should do the live feed. You should do live commentary of this.
Oh yeah. So no, what's cool about this is it's about 4 pounds on Earth's gravity, but it's only about 1 pound and oh, here it goes.
This looks like a Transformers battle about to
happen. I know. Well, okay, so just to give you an idea, it's only about 1.5 pounds on the surface of Mars because Mars has lower surface gravity, right? The rotors are about 4 feet or about 1 meter a little over 1 meter in diameter. And it has two that are spinning, counter-rotating to each other. And it's only like 1.5 feet high. And so it goes up. Those rotors are going super, super fast. Most helicopter rotors on the Earth go like 500 RPMs. These are going like 5 times that rate, like 2,500 RPM. So it's just going to go up, fly around maybe 100 feet, and then go back to its thing. But it has to do this all autonomously because the delay time between, and take some pictures of the ground shadow.
Obviously, they're controlling it with a delay, right?
Yeah, well, they're controlling it, but like the time over which the signal travels to Mars
to get back,
like 5 minutes to 30 minutes.
Yeah, I thought it was eight or 10 minutes or something.
Well, when they're in direct opposition and closest to each other, it's only 3 minutes there and 3 minutes back.
Yeah.
But when it's on the other side of the solar system, it's like 20 minutes there and 20 minutes back. But either way, you can't just go like and then wait 10 minutes for the thing to respond. So.
Well, isn't that what they do with driving the rovers? I know those people aren't there people at JPL driving the rovers, right? And I think from what I remember, they're very careful and they kind of move it bit by bit to make sure that it hasn't fallen into something or.
That's right. But they can't do that with this guy because this guy, it's only going to be up for like 90 seconds at a time.
Yeah.
So.
Do we know when
and
they're
then does it recharge or does it fully
recharge? So it has a solar panel on the top and it has like a few lithium ion batteries connected to its bottom, which are the bulk of its weight. And so it charges up, it flies for 1.5 minutes, it settles back down and it waits and recharges over the course of a few days. And then it does it again. So the whole effort is just to have, to be like a test platform to see if we can actually do this. There's no science that's really being done. It's just to see if the technology is able to do autonomous flight with a helicopter on a different planet, which is like the coolest.
Awesome. That's the coolest thing ever. Yeah, I was posting about it when it launched because all I've been waiting for is this helicopter to launch.
Yeah, it's supposed to do it reasonably soon. I haven't seen a specific date, but they're going to do 5. The goal is to do 5 separate launches in a 30-day window just to make sure that they can do it. And then I don't know. Then they'll just keep going forever. Just go all the way up. Fly into the sunset.
Not with that kind of battery life, unfortunately.
No, not you're right. Okay, so let's move on to the next question. All right, not this. Okay, Finnish astrophotographer Metsavainio recently released one of the deepest and largest images of the disk of what nearby galaxy?
Ooh.
I don't know if you guys saw this in the news. It's incredible. I'll show some pictures of it. It's really beautiful. I was like blown away. Orion.
As a side note, it's you can't underappreciate the Finnish language. It's just such a cool name, right? Orion.
Oh yeah. I'm like a quarter Finnish. My grandma was Finnish. I'm probably butchering the last name though. I just know it has this. I mean, you were in Norway, so you hear the like.
Oh, but Norwegian is completely different too.
Oh no! I know, but I know the language generally like in the Nordic countries. Both I realize Finnish is like totally different language group. It's like the Finno-Ugric languages as opposed to Scandinavian, but all of them have the kind of sing-songiness to them.
Weren't there some
except Danish? They talk with a potato in their mouth. We always said in Norway.
Oh, man.
Brutal, gosh. Wasn't Finnish? I think there were some linguistic similarities in pronunciation between Finnish and Japanese that they had found.
And Hungarian and Korean, I think.
Oh wow.
Yeah, it's totally awesome.
Yeah.
I could say like 3 words and that's it. I know sauna. Sauna is like the only word in the English language that comes from Finnish. Pretty excited about that. Anyway, great guesses here. And the answer is indeed the Milky Way. It's kind of a trick question. It's the nearest nearby galaxy. It's our galaxy. This is the image. You can download it. It's a 1.7 gigapixel image.
Wow.
That this guy's sharing. He's an artist who's taken this. It's like 2,400 hours of data over the last 12 years he did to assemble this. So this is the image. It's like, I forget, 240 degrees by by 20 degrees. This is 240 by 20. And then, but look at how it's composed. This is the mosaic that he like assembled from all his sub images. And some of those sub images took, 60 hours of just integrating on one particular target to get the depth.
Wow.
So this
is like the image?
Sub-region. What's that?
How heavy is the image?
It's like almost 2 gigapixels.
Oh, right. Yeah.
In resolution. So that image was composed of all those mosaics. It's just incredible. It's really, and the coloring, I forget, I think he's using like certain filters and such. So like oxygen 3 to pull out each alpha to pull out this and that sort of thing, pull out the different colors, but it's really incredible. Anyway, I encourage you to go check it out. Just look for awesome picture of the Milky Way. Okay. Ooh, question 3. How do you stop a zombie apocalypse? I remember hearing this just a few moments ago, I think. So what do people think? How indeed.
Are we comparing this to COVID? Is this vaccines? Is vaccines the answer?
It's
Ooh, move to Mars. That's good.
Fire. How about water? I'm surprised no one said that. I thought a lot of people always suggest BV.
Oh yeah, that's right. Because zombies are supposed to be afraid of water, right?
Yeah.
Water.
But then
I feel like aren't zombies derived from the whole idea of rabies and people who are
yeah.
Right.
Oh yeah. Oh, I hadn't even made that connection. Yeah. But there was a movie. I remember there was like some zombie movie that came out 10, 15 years ago where everyone was like, oh no, they can go in water now. They can walk underwater. This is the end.
Oh no.
So who knows?
Quarantine.
Eat them.
You have to be pretty hungry to eat a zombie. Ooh. The lull time is shorter than the revival time. I like that one. Laughing out loud time is shorter than the revival time. And that is in fact correct. You have to kill the zombies faster than their revival time, according to Max, relevant to his galactic plasma and how quickly it is created versus it's destroyed.
That's right. There was 2 answers actually. There was another answer that said it also. So there were several people. Yeah. I see. By killing it quicker. Yeah. That's good. Yeah.
Move to Mars also works though.
Yeah, I guess a bunch of these work for actual zombies.
All right. Many people know about Olympus Mons on Mars as the tallest mountain in the solar system. What body hosts the second tallest mountain?
Oh, I know this one.
Do you know this?
I do.
Oh, I'm impressed.
I think I know this. Yeah.
I didn't know this until I was doing research. That's the problem. I'm like Alex Trebek here. I know all the answers, so everybody thinks I'm the smartest man alive. But it's only because I looked them up beforehand in composing these questions.
I think I saw it while I was preparing these slides, actually. Not to give any spoilers. But well, we know that there's not that many. Let's see. There's 4 rocky planets and 4 gas giants. 2 ice giants, 2 gas giants. Are we including moons? Wait.
Well, do we know it has to be
body? Okay, so could be moons.
Yeah.
Ooh, so now,
some good
guesses. I have no idea, but I would be very interested. I mean, I was wondering, if it's not Mars, then I guess hiking on Mars is kind of boring. If there's just one mountain you can hike up.
Oh, I mean, there's other ones. This is just the tallest mountain in the solar system, right?
Yeah, I'm going to say Venus or Io.
But yeah, Cameron, you're such a hiker. Would you rather hike Mars or hike another? If you were to choose any planet in the
not a lot of shade on Mars. I guess that's true of most.
It is colder though on Mars.
Yeah, that's true. I'd like to hike on another planet. I think that'd be pretty awesome. But okay. So people generally think Io or Earth. Io is a good answer because of all the volcanoes, the active volcanoes there. Earth is a good answer, but They're both wrong. The answer I wouldn't have gotten. Answer is the second
Vesta.
largest of the asteroids in the asteroid belt, Vesta. And what's cool is here you can see it. So it's this Rhea Silvia impact crater. This is the impact crater that's like 90% the diameter of the planet. So it's called Rhea Silvia, and this is the central peak in the center. You guys can see my cursor?
Yep.
Right. Yeah.
So this is a false color image to show the elevation of it. So this is the whole object of Vesta, and then here's the impact crater edge, like rim, and then the crater, and then the central peak in the middle. So the whole object is only like 300 miles in diameter, and then the crater is like 95% of that. It's enormous.
Wasn't Vesta a planet at one point as well? Because Ceres was obviously a planet when it was, or they classified it as a planet when they discovered it. And I think then they found Vesta, because there was Vesta, Pallas, Juno, and Ceres, which I think they had sort of potentially classified some of those.
Four. They discovered. So Vesta would have been one of them. And then they were like, whoa.
This is,
there's too many asteroids. Let's not call them all planets.
And how high is it now? You didn't say.
Here, I'll show you. It's, I think it's like 22 kilometers. I'll show you in a moment. So this is not Vesta. This is, I think this is Tycho. This is just to show that same sort of structure where you have this central bulge in the center of the crater that gets kicked up in really powerful impacts like this. So in a simple crater, when things strike, it just kind of depresses the middle. But if it's a big enough one, then there's this complex crater where you get rebound from the plate, and it brings up this central peak. And it just happens to be in this Rhea Silvia impact crater that this peak is enormous. Okay, so I like this. Is
cool.
I suppose it's difficult to read the text here. I couldn't find a better version, but presumably if you go to this Reddit users page, you can find this graphic yourself. So what's cool about this is you see down here is Mount Everest, the white one. This is the tallest on Earth, right? So that's Mount Everest is what, 27,000 feet, I think. And then you see, these are all in comparison. Down here is the Burj Khalifa, the highest building, which is about half a mile in height. So that's in Dubai. Then you've got our highest peak, Mount Everest. And then you've got, here's Olympus Mons, way up here, this shield volcano. And then here's the Rhea Silvia crater. So they're about the same height, actually. And to our precision, we can't really tell. Everyone always says, oh, Olympus Mons is the tallest. But like these are close enough to each other that they're within like 100 meters of each other, at least to our ability to measure that height. So it just blows my mind that this like central bounce impact in the center of a crater is 22 kilometers in height.
What is the yellow and the black one that are right beneath it?
This one is, what the heck? I can't even read this. Buo Sole Montes on Io.
Oh, yeah.
And then this is Iapetus Equatorial Ridge on Io.
Yeah. Oh, on Io.
So Io, good people, good job, people. Io is next up, but Rhea Silvia crater, central impact crater is the one.
Do you know how? From what point do they measure? I mean, what is it defined the height? Is it from the center, or is it? Because if you already cut half the object away, right? Is it the center of mass, or is it the center of the circle?
No.
Or
I think it's from. I think it's here. Let's switch to this. I think it's from the base of the mountain as opposed to from the center. Yeah. So it's like prominence gain of prominence. Although
that's interesting.
Maybe not.
Maybe it's
then because Everest is in the Himalayas.
I just wanted to say, then on Earth it wouldn't.
So
be
maybe it's just maybe it's height above its average, the average equator or distance from the core.
Average surface, yeah. I thought for some reason I had read about one on Venus yesterday, but actually no, because like I was mentioning, it's interesting. Venus's surface was entirely resurfaced. It's a super young surface. It kind of looks like it's been turned inside out. And so, actually, I can't remember if there are, I mean, there's some mounts of sort. There's some interesting geological features on Venus. But yeah, I guess no tall mountains there because it's probably too young also, and it doesn't have tectonic plates.
Yeah. Yeah. I don't know. I don't think a lot about surface morphology of the
You should. This is why we should send more missions there.
Okay, let's go to the next question. Ooh, on what planet would you be most likely to meet a Wookie? A Wookie. Like
Wow. I see we reached the Star Wars portion.
yeah, I always have a Star Wars question. I know a lot of people are like, Star Wars is dumb. And
No
to
way.
that I would say, you are dumb. Go back to fourth grade. And then we'd get into a big brawl about things like that.
Better than a Star Wars versus Star Trek battle.
Yeah, I'm trying to get. We're potentially going to have an astronomy on tap that has a science of Star Trek and a science of Star Wars talk or something like that. But I'm still arranging that.
Will the quiz be all Star Wars and Star Trek questions?
I don't know. Maybe
reverse it. Yeah, one non-Star Wars. Right?
Max, do you have a preference between Star Wars and Star Trek?
Not. I think Star Wars, but I'm neither. I have to admit, I'm neither really. I'm in astrophysics, but I'm not really a big fan of either. Shame on me. I know it's.
That's okay. That's okay. Yeah. Planet Nerd. Yes. Crowd resident.
Enceladus.
Yeah. Some good guesses here. Most people are going with Endor. Endor is the moon of Endor is where the Ewoks live, but but
there's, I mean, if you count the number of people saying Kashyyyk, it's like a lot. It just differ
it's just different
spellings.
That's right. So that there is somebody got the proper pronunciation or not pronunciation. The proper
Kashyyyk.
spelling there. It's 3 Y's. Kashyyyk. It's this this foresty, jungly kind of planet where the Wookiees live in the high canopy. They're the only sentient species there, but there's a lot of other species down on the surface. I think this shows up in episode 3, because there's I don't want to ruin what happens in Star Wars.
No spoilers.
It's only been out for 20 years.
It's not possible to spoil.
Bad things happen in that one on Kashyyyk, so I encourage you to watch it. But anyway, we'll move on from there. What object in the solar system has the most eccentric orbit? Okay, something that we were hearing about a bit with Laura May's presentation. What do people think?
So eccentric again is how flattened that circular, the elongation, yes, of the orbit is.
Yeah. So yeah, don't look it up. Just give it your best guess. Humans have
humans are pretty eccentric.
Planet 9. Ooh, that's a good one. Comets, good. Pluto. Ooh, I love 332 phone number. Nice.
We know that HC332 person looked it up and copied it. We know you didn't type this.
Maybe that's what they strive to memorize over the course of
It's like that HD planet I was mentioning HD 20-something B.
Mm-hmm.
Surfboard.
Surfboards are elongated.
That's true. Yeah. Kind of the shape, actually.
So the answer to this is that it kind of depends. It depends what you mean. So we asked, what was the highest eccentric orbit in the solar system? This is much like the stuff that Laura May was showing in terms of showing different orbital eccentricities. So red is the circle, so it's a 0. And as you go towards pink, you increase that eccentricity. And these are the orbits that they take, even though they have the same time, the same period that it takes to go around the sun. This is just another way of kind of showing that.
Oh, that's a cool graphic.
Yeah, I thought it was kind of cool.
Yep.
So yeah, when you get to E equals 1, you're on a parabola. So you're not actually bound, gravitationally bound. And you can go above E=1.
You have hyperbolic orbit. Yeah.
To hyperbolic orbits. Yeah, too,
Yeah.
but they're not really bound. So if we're just talking about planets, you mentioned this in your talk, right, Laura May?
Yep.
Mercury.
Mercury.
You've got Mercury, and the distance when it's closest to the sun is 0.3 the distance from the Earth to the sun, and so 0.3 AU. And when it's farthest, it's at like almost 0.5 AU. So there's some.
Yeah, in fact, the fact that it has this extent, so Mercury hardly has any tilt to the obliquity that we were mentioning. I think it's like 0.1 or something, or 0.01, or but because it has that very eccentric orbit, it actually has seasons because of it. So actually you can have seasons without having that axial tilt that Earth or Neptune has, but it will depend on having a more eccentric orbit.
Yeah, that's true. Okay, so the answer, if you're just talking about planets, is Mercury. But if you extend to non-planets, well, Pluto. Pluto, a dwarf planet, it has a higher eccentricity. And it's also out of the plane. Pluto's a kind of a wonky dude for a bunch of reasons. Yeah. But then if you extend that to not even be dwarf planets, you can get really, really high eccentricity. So comets tend to be these super, super highly eccentric things. Like Halley's Comet is, we said 1 is when it's a parabola and it's not bound at all. And this is getting up pretty close. And this is actually cool to see, because we can see that right now Halley is almost at its aphelion. It's so far away from the Earth. Yeah. The sun and the Earth, I guess, but mostly the sun.
Yeah.
Body here, and that hopefully I'll still be alive when it comes back into the inner solar system in like 50 years. So we'll see.
It's a good comment. It seems to really cycle well with like human lifetime. Roughly, everybody has a chance to see it at least once, right?
Yeah, I remember seeing it when I was a little kid, when it passed through, but giving away my age that I'm a senior citizen here. But,
we also had, I saw Hale-Bopp.
Hale-Bopp,
that was in what my mom showed me Hale-Bopp in, I think 95 was it, or something like that.
Yeah, it was
right.
around.
I remember.
And that was another really, really beautiful one.
And super eccentric as well.
Yeah,
but I think that comes back every like 400 years or whatnot,
that one
or
has
200.
That one has a much longer orbital period.
And then, of course, the real answer are the ones that aren't actually bound. So this is that comet Borisov, which you guys probably were able, if you went out, 2 years ago with a telescope, you could probably make this out in the sky. And it has a hyperbolic orbit, so it has this super high. I really like this image, which shows both Oumuamua, the interstellar asteroid that everyone is making a big kerfuffle about, and Avi Loeb thinks is actually aliens, but is probably not. And then Comet Borisov, which even has an even higher eccentricity orbit. There was a really, relative to Oumuamua, there was a really interesting paper put out last week about that has a more relevant explanation for, or potentially probable explanation for, what Oumuamua is, and that is that it's a big chunk of solid, is it nitrogen? Like solid frozen nitrogen, and it's been evaporating that it was potentially ejected from an object, a Pluto-like object in another solar system, and that it's been evaporating preferentially along both sides. I think the description I read that was really nice was like a soap bar, intrinsically thinner and thinner and narrower as it gets eroded down. Cool. So I haven't read that paper, but it's
does the evaporation because there were these, when you evaporate, because it kind of seemed to accelerate, right? Does it explain that is there enough
I think
momentum exchange?
Explain that in terms of outgassing, but
that's
but
cool.
I don't know. Again, I need to read the paper. Anyway, it seemed like a nice explanation for it instead of having to invoke aliens.
Right. Yeah, you should have an astronomy on tap on that. That's a good topic.
Oh no!
I mean, not aliens, but the natural explanation.
Yeah, no, that's a really good idea. I mean, I know I even got flack from someone a couple of months ago because I spoke derisively about the alien theory. I find it very frustrating that Avi has taken this position so outwardly when there are like
there's a lot of better,
there's a lot of potential other explanations for
Yeah.
something, and just because it
Right.
doesn't fit our model at this point in time, you don't just throw up your hands and say, well, it must be aliens, boys, must be aliens, ladies. It's really problematic to do. And I know a lot of other scientists agree on that front, and Avi's taken, you know, think of the opportunities out there. Not that he speaks that way, but like I find it very frustrating that he cries foul, that everyone is like down on him for taking this position. But I just don't think it's the scientist's way to make bold claims without bold evidence.
I mean, that seems similar to past explanations of when we didn't understand something and we said it was religion, it was God, or that now it's
kind of
thing.
thing.
And now it's aliens. Seems like a similar thing.
So anyway, he's entitled to his opinions. I just don't agree with them, and that's okay too. So anyway, I'm not trying to get too political here.
And you get a lot of UFO people coming in.
Indeed. Okay. So next question. Okay. The sun will eventually turn into what? Got a few different options here.
Gray wizard.
What's that?
Oh no, I laughed at the gray wizard.
Oh yeah, the gray wizard, a well-known astronomical object. Okay.
That's cool. We see them voting live. I never used Menti this way. I like it.
It's a nice way to see how people are voting. Oh, somebody's down with the gray wizard.
Was this inspired by Gandalf the Grey? Are we doing a Gandalf the Grey, Gandalf the White thing?
Oh, Gandalf the White. Well, Gandalf the supernova. Gandalf the neutron star. Sauron the black hole, maybe. I don't know.
It's in the unreleased version.
Yeah, that's in the unfinished tales.
Yeah, it's Peter Jackson's next project.
That's okay. So people generally seem to agree that it is not the gray wizard. It's certainly not a black hole. My goodness. People think it's a white dwarf. So this was kind of a two-part response. So we believe, based on stellar evolution models, that the sun is not massive enough to turn into a supernova and eventually either a neutron star or a black hole, that it's lower mass. And so what it will turn into is something like this. This is the, I meant for this to be the Ring Nebula, but I think this is actually the Helix Nebula. So this is a planetary nebula, and planetary doesn't really mean, it doesn't have anything to do with planets. It's a misnomer, much like a lot of the things in astronomy. We're stuck with these words that don't
Metals.
fly anywhere. What's that?
Like metals.
Like metals. Yeah. Or early type galaxies, late type galaxies, early type stars, late type
population 1, population 2 stars, etc.
The magnitude system. Anyway,
Oh,
so what's going to happen? So the answer is both planetary nebula and a white dwarf. So basically, I've got this cool video that I found that somebody put together. Let's see if we can. Oh, oops. So you've got your sun, which grows late in its life. It becomes a red giant. It essentially puffs up, and its outer surface becomes cooler and therefore redder, because the cooler part of a flame is like the red part of a flame. So this is something like Betelgeuse or one of these other, and then it sloughs off its outer layers entirely, and they kind of fly out and glow, and you're left with a white dwarf in the center. So I really like this animation, actually. It's pretty sweet.
That's cool.
You can see this video is actually more focused on these detailed structures that you can see in the Helix Nebula, which I guess are just like clumps of gas and dust and that are dense enough that they're kind of being pushed outward by radiation. Well, that's too bad. We went to this. Would have been nice.
Are they falling? Are these like globules falling back in, kind of?
No, I think they're globules that are just falling out more slowly and not being ablated quite as quickly as the rest of the material that's flowing out.
Right.
But that's something like what's going to happen to the solar system in like, what is it, 5 billion years or so?
Yeah.
I mean, don't worry. I'm not planning to live that long.
Do we know what forms the smaller black holes, in fact? Because I was trying to remember what stars or what gives birth to the small black holes. You know, those they
What do
have
you mean by small? Like,
you know, we have ideas about the miniature black holes and that kind of thing.
Well, Max,
Yeah, there's a bunch of theories about primordial black holes,
Exactly.
which are interesting, right? That's black holes created really, really early in the universe, basically just after the Big Bang, and yeah, there were it's very interesting theory. So in fact, there were some ideas, you know, how much you can dark matter can be made from that, and this kind of thing. But I mean, there's interesting constraints on these, for instance, from the Hawking radiation, right? Because each black hole evaporates. You can actually set a limit on how small a black hole you can create early in the universe for it still to exist. And then there's other cool constraints I think are really remarkable. They use telescope and stare just at a fixed point really long, and then they say, well, if there would be black holes, we would see them pass, now and then. And just from not seeing something, you can actually put cool limits on these sizes of black holes, which I think is remarkable, right? You're just not seeing something, I think it's nice.
And then, well, I mean, I know there was some concern that the LHC or particle colliders
was going to create
could potentially cause like
a miniature black hole.
But Hawking radiation, the rate at which these things evaporate is very dependent on the mass of those objects. And so if you have really, really tiny, minuscule black holes, I think the time scale over which those evaporate from Hawking radiation is really
super quick. Yeah.
And so, there's actually a really good book, a science fiction novel called Earth, that's about this. Oh, I have it.
But I think the size they detected so far are much bigger, right, than this.
Yeah.
Oh yeah. A microscopic black hole has accidentally fallen into the Earth's core, threatening to destroy the entire planet within 2 years. Some scientists are frantically searching for ways to prevent the disaster. Anyway, it probably isn't a concern because I think David Brin wasn't aware of Hawking radiation.
What's the title of it? Earth?
It's called Earth.
Ooh.
Anyway, interesting novel nonetheless. Ominous, yeah. But yeah, the answer I think is right, that Max said, is just there's a bunch of theories for primitive black holes or primordial black holes on a variety of different mass scales, some of them small, some of them larger, but at some level that I think most models rule that out because of microlensing surveys and that sort of thing where you'd be able to pick this up. But I think there's still some
windows left and they close them, and these windows are somewhat interesting. Some people still believe that dark matter is essentially these black holes, but I think windows are very fast closing.
Yeah, on that theory.
Okay, we only have a couple questions left. Where is my? Here we go. Okay. What is the name of the well-accepted theory describing the origin of the universe as a singularity, coined by one of its detractors? Ooh. Ooh. I think. Big Bang. Okay. Stringther. Big fan of Stringther.
Big Bang gets bigger.
Appropriate.
Wow.
Even bigger.
It's great. The dynamic is fitting. Big Bang Theory.
Okay. Yes, indeed.
That TV show.
That TV show set at Caltech following postdocs. I can tell you that my life, I've only seen that show a couple of times, but my life is nothing like the life of Sheldon, despite the fact that he is set at Caltech as a postdoc, much like me.
I think you're more similar to Leonard, the character of Leonard.
Oh, I'm like Leonard? I don't know if that's good or bad.
That's good compared to Sheldon.
Oh, okay. Okay.
Big.
The Big Bang is the correct answer. And yeah, I think it's an interesting story. So Fred Hoyle, who, was an astrophysicist in the early to middle part of the 20th century and did all kinds of good science. Basically, he was an advocate of an alternative theory called the steady state theory, which, in some ways, I think is the most intuitive theory, right? Is that the universe has just always been around and it's infinite in its extent. And, that makes sense. I think that's at least what I would think by default, if not presented with other evidence. And he and some other scientists were big proponents of this. And he actually went on like a radio show and was like speaking derisively about this new theory. And he's like, as if the universe appeared in a big bang or something like that. And people were like, oh, that's a good name for that theory. So it's funny that he, being one of the biggest detractors of this theory, was actually the person who named it.
That's pretty good.
That's funny. Yeah. Didn't know that.
Now, we have major pieces of evidence that suggest, it fits with a lot of evidence, whether it's the expansion of, galaxies traveling away from us, or the abundance of light elements like boron and beryllium and lithium that weren't formed in the interiors of stars. They were only formed right after the Big Bang in nucleosynthesis or the cosmic microwave background, that sort of thing. So things all fit really well. I think there's one more question. Let me see. Okay. Oh, where on the moon did Apollo 11 land? What do you guys think?
Ooh, I think I know this one.
I have no clue.
I don't want to give spoilers to the people participating.
Yeah, no spoilers. You can answer it in your thing though.
Oh yeah. Crater.
Talking about the space mission landing somewhere and sending cool pictures, you showed this cool movie from the this cool image from the Soviets. You said that's pretty impressive. So they landed at what time was that on Venus? You showed.
Oh yeah, the Venera mission. Yeah, I think that was in the 70s, and they actually sent quite a few things down there, and their things survived long enough to take a couple pictures. Yeah, which is amazing given the temperatures and given the time that it was.
The time, I just said it's like ages ago. Right?
It was certainly, it was the Soviet Union. So I think it was around the 70s. And they're actually sending something back there soon, because I remember the people working on the phosphine theory in the atmosphere of Venus were, someone was suggesting to them to piggyback on that mission to get more data. But yeah, I think they're sending something to Venus in the coming 2 years or something like that.
Wait, who is? The Russians are, or we are?
I think the Russians are. I think the Russians are sending something back there. Yeah.
Yeah, I wouldn't want to land anything on 1,000-degree surface. That seems problematic.
Yeah, especially a surface that's constantly resurfacing itself.
Good guesses all around. On its feet, indeed. The mushroom-looking Sea of Tranquility is in fact the answer. Here are the landing sites for all 6 of the Apollo missions that landed on the surface. Of course, Apollo 13 had its issues, actually landed. It just slingshotted around. But you can see Apollo 11 here, indeed, on the Sea of Tranquility. 12 is over here in Oceanus Procellaris, the Ocean of Storms, I think. 14, Hadley Rill area. I don't remember all of these, but 15, 16, 17. Yeah, here you can see some of those things. Oh, so cool. These are named. Obviously, these were named. Well, maybe not obviously. These were named originally.
Wrong names, right? It's like C or something.
Yeah, it's because Galileo, was the first to use a telescope to look at the moon, and he's like, "Oh, look at all this stuff. Those look like seas and oceans, so I'm going to name them such." So it's like, Mare Tranquillitatis and Mare Serenitatis. And
did Percival Lowell do the same? I know someone was selling a globe of those names that had all those names that Percival Lowell gave to the canals on Mars that he thought about. Yeah. And I don't know if we kept any of the names that he used at the time for those regions. Or
well, there's Valles Marineris, which is the largest canal system, like
the largest canyon.
Yeah, canyon.
Yeah.
I think in the solar system, but certainly on Mars, and you can see it on the images of Mars.
Yeah,
it's really cool. So presumably he was the person to name it.
Yeah.
Anyway, reached the end of the presentation. There we go. Thank you everyone for all the questions. Do you guys have anything that you guys would like to add here before we adjourn? I guess it is 8:30.
Thank you for
well, just thank
us.
you. Yeah, thank you for inviting, and thanks for organizing.
Thanks,
it's been
thank
fun.
you guys for joining. This was great. Thank you, audience, for your participation. As I mentioned at the beginning, we have a lecture this Friday at 7 p.m. Pacific time, given by Professor Sri Kulkarni on why technology is actually the driver of astronomy instead of ideas. A very controversial idea, but interesting nonetheless. And then next Monday, we'll have Astronomy on Tap entirely in Mandarin Chinese. I will not be the host because I don't speak Mandarin Chinese.
Very exciting.
But I encourage you to check it out if you're a Mandarin speaker. If you're not, spread the word to other Mandarin speakers. And we will, within a few days after it's recorded, of course, you're welcome to tune in. I think the topics are super interesting. One is on killer asteroids. The other is on, what was the title? Going to the ends of the universe to study its beginnings. And that's all about using telescopes at the South Pole to study, like the BICEP mission, and maybe even the South Pole telescope to study the cosmic microwave background and basically what's happening that we know about at the beginning of the universe from the cosmic microwave background. So very interesting. Those should be either dubbed or subtitled within a few days. We'll try and post that so that you can check back. Even if you, like me, are an ignorant person who doesn't speak Mandarin, then you should be able to watch that. And then, we'll have more events in the coming months, but I'll post stuff online when those are available. So
are there any French astronomy on taps?
I haven't hosted any. There is one in Montreal. That's bilingual.
Oh, cool.
So Montreal has one. I don't know if they've been doing it since the pandemic has gone down, but I know that they regularly do one. Other international, was there one in Oslo?
Yes, there was one in Oslo. It was the first in Scandinavia.
Was it in English?
Back then? Yeah, it was in English. But sometimes in Norwegian if we got Norwegian speakers, but usually it was in English. There's a lot of expats around, but it was fun.
There's one in Budapest. There's one in, I think there are a couple in the Netherlands. I think there might be one in Germany. I don't know of any.
People, they're like all around, right? You can go to, there's some webpage. What is it that?
That collects
all of them.
Yeah. So if people are interested, go to astronomyontap.com. It lists all the events that are going on, which previously wasn't really relevant unless you were in a particular location. But now that it's the pandemic, lots of them are broadcast live over YouTube Live. So you can go and click and, 10 days a month, you could go watch some sort of broadcast of something live, or you can tune in after the fact and check out the recordings of them. So there's some really good ones. I think there's one tomorrow night from Cambridge University in the UK. They always have very good ones.
Oh, nice.
So, or at least sometime this week. But anyway, lots of good options. And I encourage you guys to check it out. So thank you, audience. Thank you, Laura May. Thank you, Max. And we'll see everybody maybe this Friday, maybe next Monday, maybe never. I don't know. Whatever floats. Thanks for joining us, everybody.
Bye.
Bye.